At the heart of modern physics lies a paradox. Two of our most successful theories, quantum mechanics and Einstein's theory of relativity, describe the universe in fundamentally different ways. One is probabilistic and observer-dependent, the other deterministic and geometric. Yet, both challenge the classical assumption that reality is objective. Science has long treated objectivity as an absolute truth. But when we examine the deeper implications of relativity and quantum theory, we find something startling. Reality is not purely objective, it is subjective. Relativity teaches us that space and time are not universal constants but depend on the observer's frame of reference. Meanwhile, quantum mechanics reveals a world where particles exist in superpositions until measured, suggesting that observation itself shapes reality. Far from being contradictory, these theories share a common root. They both imply that the observer plays a central role in defining what is real. So this is the first philosophical question that we need to reconcile in order to solve the observer effect problem. Science, at its core, is the study of change. To measure change, we rely on two fundamental tools, space and time. But here's the problem: there is no universally accepted definition of either. Are space and time physical entities? Are they relational? Are they emergent properties of something deeper? Worse still, we try to quantify dynamic phenomena using static units, assigning fixed values to things that are inherently fluid. This is so because both space and time actually measure change, but in order to measure the change, we assign function of constant to change, i.e., we assign fixed value to space and time, which are tools to measure change, by various matrix system of measurement. This creates a paradox. We use constants to describe change. This is the second philosophical question that we need to reconcile in order to solve the observer effect problem. Kurt Gödel showed that any formal system powerful enough to describe arithmetic will contain truths that cannot be proven within that system. This implies that causality itself may not be provable, it is assumed rather than derived. Yet science proceeds under the assumption that causality holds, verified not through logic, but through experimental repetition. This echoes David Hume's skepticism. Causality is not something we observe directly, but something we infer. So this is the third philosophical question that we need to reconcile in order to solve the observer effect problem. So we are left with a choice: accept certain foundational principles as true for the sake of building meaningful models, or reject them and lose all predictive power. Science seeks to uncover the laws of nature. But perhaps we've been playing with the wrong rules. Reality isn't broken, we've just misunderstood the game it plays. That is why I say the observer effect is a philosophical, not a mathematical problem. By embracing the subjective nature of observation, the relational essence of change, and the inherent limitations of causality, we can begin to see a unified picture of reality emerge. Gödel told us that no system is complete. Wittgenstein told us that meaning is context-bound. Quantum mechanics told us that observation matters. Einstein told us that space and time are relative. Now it's time to put those pieces together, not as separate ideas, but as parts of a single, coherent whole. And the key to unlocking it begins with asking these philosophical questions. If your mind enjoyed this, engage with Braingasm pages, like, share, comment and subscribe.